This is my actual differential equations exam 1. I added a word problem at the end because I forgot to do that, but otherwise it's exactly the differential equations exam I gave. So it would be nice to see how these questions are solved. Let's do the first question. I need some function cx squared, which is a solution to this. That means when I set y equals to cx squared and plug that into the left side, it should match with x squared, right? However, as you can see here, this y prime and y double prime requires me to differentiate. So let me differentiate to cx, and then y double prime would be differentiate again, it would be 2c, right? So now plugging these into the left side, I get, what do I get? I get, well, it's this side, but when I see y double prime, it's going to be replaced by 2c, and y prime will be replaced by 2cx, and y will be replaced by cx squared. Okay, and let's simplify this. This would be 7 times 2 is 14, so it would be 14cx squared. And then minus 5 times 2, 10, 10cx squared, and plus 5cx squared. And I guess I'm getting 9, right? Let me check again. 2, 14, 10, 5. Okay, so 14 plus 5 is 19 minus 10. That's 9cx squared. And because I need this to equal to the right side, I must have 9cx squared equals to x squared, and that says that 9c must equal to 1 after dividing by x squared both sides, and I see that c is equal to 1/9. Okay, now since the question was just asking for the value of c, this will be the final answer. But if you want to know what the meaning of this is, that we see that 1/9 x squared is actually a particular solution for this one. That's the achievement we just made. Okay, second question. Solve y prime equals to x squared cosine 3x. Well, this is just a simple integration question, because if y would be the integral of this x squared cosine 3x, and because there's no y on the right side, this is doable. You can actually integrate this, and this is actually something that you can integrate using the tabular integration. So now let's try to make a table. So I have x squared, x2x, so I'll need this much. So tabular integration has plus or minus, and I need to put d, and over here I need the integral. On the d side, I'm going to differentiate x squared, so that differentiates to 2x, and 2x differentiates to 2, and 2 finally differentiates to 0. So put 0 here. So x squared differentiates to 2x, 2x differentiates to 2, 2 differentiates to 0. On the other hand, cosine 3x has to be integrated, and the integral of that is sine of 3x. But because of this 3 in front, you need a 1/3. So it's 1/3 sine of 3x. And then when you integrate this again, you're going to get negative 1/9 cosine of 3x. And integrating, every time you integrate, 1/3 keeps popping up because of this 3. So if you integrate for the third time, it'll be 1 over 27, and it'll be negative 1 over 27 sine 3x, and then you're going to get plus, and then minus, plus, then minus. And once you have that, let me just make it smaller because it doesn't have to be this big. Let me see. Make it smaller. Okay. So once you have this table, then you can multiply in this format, right? And then like that, and like that. Okay, and the result is that you get well, x squared times 1/3 sine 3x. That's the very first thing we have, and then negative times negative is positive, so it'll be still positive. And 2 times 1/9 will be 2 over 9 x cosine 3x. Let's move the 1/3 in front. That's better. So I'll put 1/3 in front and put the sine 3x here. And then the last one is positive times negative, so it's negative, and you have negative 2 over 27. And then it's just sine 3x, and then plus c. So that's the result of this integral. By the way, I have other videos about doing this tabular integration, so please watch that, because you actually have to do something on the last row if it's not 0, which I didn't do here. Yeah. So I just want to point out that this last row you have to multiply and integrate, but we didn't have to do that because it's 0. Okay, so that's the answer for the second one. Okay, question number 3. This time you can't simply just integrate the left side because there's y on the right side, so you need to somehow move all the y's to one side and move the x on the other side, and that's called separable, right? So here's what I want to do. Hint says you have to factor the right side, so let's factor the right side. We can factor this because there's a common factor x. So if I factor out the x, it's 1 plus y squared. And then I'll also rewrite y prime as dy over dx, because then I can move the dx to the other side while dividing by 1 plus y squared on the left side. So you're going to get y over 1 plus y squared, and then times dy equals x times dx. And then you integrate this. If you integrate both sides, you get, well, let's just copy this and put integral signs. So you have this integral sign and also integral sign. And the important formula here is that if you integrate f over f prime, f over f prime, then you get ln, sorry, I got the f prime, it should be f prime over f. If you have that, then you get the ln of the denominator plus c. And that's a really nice formula that you get to use a lot of times, so you should memorize this. And in fact, the left side looks very much like that. The only difference is if this was 2, then it is the derivative of the denominator, right? So what you want to do on the left side is to multiply 2 on top, but put a 1/2 in front, so that it's still the same thing. if you multiply by 2 and divide by 2, it's still the same thing, right? And this, by use of this formula, we can rewrite the left side as ln of 1 plus y squared. And then the right side, if you integrate x, it's 1/2 x squared plus c. Oh, I forgot the 1/2 here. And then you still have to solve for y, so let's try to solve this for y. I want to first multiply by 2 both sides. So the result is that we have ln of 1 plus y squared is equal to x squared plus c. And at this point you might say, oh, shouldn't this be 2c? But it doesn't matter because it's just some constant. 2c or c, they just mean some constant. It could be any number, okay? So this could be any number here. And then to get rid of the ln, we have to take the exponentiation of both sides. So we take this one and we put e and put it as an exponent. And again, the same thing, e. Then it should be plus c over here. And then e and ln cancel, so you have 1 plus y squared. And there's another trick here. If you have e to the x squared plus c, that can be written as e to the x squared times e to the c, which can again be replaced by c. So you can just, e to the c is just some constant, so we can rewrite that as some constant times x squared. And then we still have to solve for y, so I'm going to isolate y squared by subtracting 1. So it's this thing minus 1. And then finally you have to take the square root so that you have y equals to plus or minus square root of this right side. But that's not it, because we still need to satisfy the initial condition. So let's see, if y of 0 is 1, let's see what that means. First, because it's plus, I can't have the minus, so it should be strictly the positive one. So it must be the positive one. And then also when 0 is plugged in, I need it to equal to 1. But 0 is plugged into x, so that's just 0, which is same thing as equals to square root of c minus 1. C minus 1. And therefore c must equal to 2 for this to work. So you put that back into the original equation with a positive sign, and your final answer, the real answer to this, would be positive sign, and this would be 2. And that's the final answer. Okay, another first order differential equation. But unfortunately, if you try to do it like the previous one, if you try to separate the y on one side and x on the other side, you will see that it doesn't work. So at first you have to see what kind of differential equation it is. And you see that y prime is by itself, it's first power, and some function of x is multiplied, right? Y is also first power, some number is multiplied. But y and y prime are not multiplied, they're both power of 1, so that's first order linear. For a first order linear differential equation, you need the standard form. Standard form of first order differential equation, standard form, is y prime plus px y equals to qx. And to solve a first order differential equation, you need to know the multiplier, whose formula is m of x is equal to e to the power of integral p of x dx. Okay, so that's the formula that you have to use. And this can only be used once you're in the standard form. Okay, so I have this one, which is not in the standard form, and if you compare this with the standard form, the only difference is that y prime has x, whereas here y prime is by itself, right? So you should divide by x to get the standard form. Divide by x to get y prime plus 2 over x times y equals to 1 over x e to the x squared. Okay. And once you have that, we can now identify that 2 over x is p. So we can use this formula with p of x now 2 over x. Now 2 over x integrates to 1 over x integrates to ln, so this would be 2 e to the 2 times ln of x. But the problem is, this itself is not going to get you anywhere. You really need to know how to simplify this. How do we simplify it? Well, it's tempting to cancel the e and ln, but this 2 is in the way. So you first have to get rid of this 2, and the way you do it is by making it jump over the log like a frog. So I call this the frog over the log rule. You need to get rid of this 2, remove it from between e and ln, so they can just cancel each other. All right, so we have e to the power of ln of x, and the 2 is now moved inside the log. See, this 2 jumped over the log, and now it's here. And because 2 is no longer between the e and ln, now e and ln can cancel themselves, leaving you with just x squared. So we find that the multiplier must be x squared, and once you find the multiplier, that has to be multiplied to the standard form, not to the original one. If you multiply x squared to the original one, you don't get anywhere. You have to multiply the multiplier to the original one. So if I take this and multiply x squared to each and every term I see, the result is that I get x squared y prime plus x squared divided by x is x, so you get 2xy equals to x times e to the x squared. And the big purpose of multiplier is that the left side becomes a product rule of some derivative, and you can check that the left side actually is equivalent to the product rule applied to the following derivative, x squared times y prime. So these two are different. Here y is differentiated and you just simply multiply by x squared. Here x squared and y are multiplied, and then you have to differentiate, and because it's a product of two things, when you differentiate you need to use the product rule. And if you do use the product rule, you'll see that it gives you two terms, and that has to equal to this right side. Now integrate both sides. The left side is easy. When you differentiate and integrate, you just come back to the original one, right? So that side is easy. However, to integrate this, you need to use the u substitution. So let's try this. U equals to x squared, which gives you that du is equal to 2x dx. And if you solve for dx, you get dx equals to 1 over 2x du. Using this, you can rewrite the right side integral as this will, x squared will now be u, and dx will be 1 over 2x du, where that means it's 1/2 of integral. And you can see that x and x cancel, so those don't appear anymore, and you just simply have integral of e to the u du. And e to the u integrates to e to the u, so it's 1/2 e to the u plus c. And because u is something you introduced, you have to go back to the original function, which is e to the x squared. So e to the u should be e to the x squared plus c. And so here's the result of the integral on the right side. You end up with just this. And because you still have to divide by, you still have to solve for y, we have to divide by x squared. And that results in y equals to 1/2x squared e to the x squared, and then c over x squared. Now, some people think, oh, well, c is just some arbitrary number, so maybe c over x squared can be just replaced by c, which shouldn't be done, okay? Because c by itself is a constant which doesn't change with the values of x changing, but c over x squared is a function of x that changes as you change the value of x. So you can't just say c over x squared is just some constant. It's actually something that does change with respect to x. So don't put c instead of c over x squared. So this is the correct answer. Okay, number 5. Show that the above differential equation is exact. Well, when it comes to differential equations, you're really thinking of this part as f differentiated by x, and this as f differentiated by y, for some function of two variables x and y. And because f differentiated by x and then y is same thing as f differentiated by y and then x, if there really was a single function responsible for generating both of these things, if you take the very first thing and differentiate by y, so if I do partial with respect to y, because this is already differentiated once by x, and then if I differentiate that by y, let's see, that's a partial derivative, so you're treating all the x's as constant, so this will be just e to the x, and then if you differentiate e to the 3y by y, it's 3 times e to the 3y. And this 3 is due to the chain rule. You have to take the inside function outside and differentiate. And because 3x squared is considered as a constant, if you differentiate, it's gone, so it doesn't show up here. Okay. On the other hand, if I take this second part and you differentiate by x, then e to the x differentiates to e to the x, and e to the 3y is just considered as a constant, and 3 is considered as a constant, so you're really just differentiating x. So if you differentiate x by x, that's just 1, right? So you're just left with 3 times e to the 3y. And they do match. They match, and hence this is an exact differential equation. Alright, so now we have to solve the differential equation, and that means you have to find one function whose total derivative is equal to this left side, right? So let's see, your function f of xy must have been, you can recover the function by undoing the derivative by x, right? So we do this and then you integrate by x. And unfortunately for integrals, we don't have a different symbol for partial integration and straight up integration. But here, this integral should be interpreted as a partial integration, meaning that you're treating y as a constant. So you're just thinking of this as a function of x, and y is constant, and you're integrating as a function of x. So e to the x integrates to e to the x. there's no change there. E to the 3y is a constant, so if you integrate by x, it just obtains this x. And then plus, if you integrate 3x squared, that's x cubed. Okay, and then, because this is a partial integration, you can have a function of y instead of a constant function. So if you take this and differentiate partially by x, this g of y is considered as a constant. It goes away, and you do recover something inside. So an important thing that you have to remember is that if you do a partial integration, then it's not plus c, it's a function of y if you integrate by x. On the other hand, if you integrate by y, then you will end up with a function of x. Okay, so let's do this other one. Fx comma y must be also the integral of the second part by y, and if you integrate e to the x by y, that's e to the xy, plus if you integrate e to the 3y, the chain rule says 1/3 should come up, canceling this 3, so you're going to have x times e to the 3y, and then plus some function of x this time for the same reason. Okay. And now the question is, what could h of x be, and what could g of y be, so that these two different looking expressions actually mean a single fxy. You have to harmonize the two different accounts of description of this same thing. And we see that if f of x comma y is this thing, and if hx is this x cubed, and g of y is 0, then everything works out. So I can kind of see that g of y being 0 and h of x being x cubed makes everything work, and this should be the final answer. But wait, that's not the final answer. If you stop here, you don't get full credit. F was something that we introduced in order to think about where this equation came from, but if you were to do the integral of both sides, the left side integrates this to this one, but if you integrate 0 on the right side, it just gives you a constant. So that's the correct answer. Okay, show that sine 3x and cosine 3x are linearly independent using the Wronskian of two functions. Well, the Wronskian of two functions is a determinant of each individual functions. You have this, and then the next rows are created by differentiating these separately. So if you differentiate sine 3x, you're going to get 3 times cosine 3x, right? On the other hand, if you differentiate cosine 3x, you get negative 3 times sine 3x. Now, these straight lines means you have to calculate the determinant, which is computed by doing a times d minus b times c. So you get sine 3x times negative 3 sine 3x minus bc, so cosine 3x times 3 cosine 3x, and we see that if you simplify this as negative 3 times sine squared (3x), and the second one is negative 3 times cosine squared 3x. And to show that it's linearly independent, you have to show that this is never 0. But it's hard to see why this is never 0, right? And so you need to do one more step, which is to factor the negative 3 out and see that the resulting formula is sine squared 3x plus cosine squared 3x, And we know that sine squared plus cosine squared is 1. It's always 1 as long as these two angles are same, right? So you end up with negative 3 times 1. That's equal to negative 3. Okay, so you see that this is not equal to 0, and therefore the two functions are linearly independent. Okay, solve the initial value problem. And now this is a second order homogeneous differential equation. So to solve it, you need to write down the characteristic equation. So r squared plus 2r plus 5 equal to 0. And you can just use the quadratic formula to get the value of r, but I think it's easier in this case to just do the completing the square. So you get r plus 1 squared plus 4 equals to 0, which means r plus 1 squared is equal to negative 4. And taking the square root of both sides, you get r plus 1 equals to square root of negative 4 is 2i, because taking the square root of a negative 1 gives you I, right? So you end up with plus or minus 2i, which says that r is equal to negative 1 plus or minus 2i. Now, in the case when you have a complex number a plus minus bi for the solution of the characteristic equation, the general solution, the solution in general, looks like e to the power of the real part, negative 1, negative 1t, negative 1x, so it's just negative x, times c1 times cosine of this imaginary part 2. 2 is the imaginary part, so it's 2x, then plus c2 sine 2x. So that's the general solution for this differential equation. But we still have to figure out what c1 and c2 must be so that it satisfies these two conditions. So first of all, y of 0 is equal to this thing. When you plug in 0, you get e to the 0th power, which is 1, cosine 0, which is 1, and sine 0 is 0. So e to 0 is 1, it doesn't do anything. 1 times c1 is c1, 0 times c2 is 0, so you just get c1. And because y of 0 is equal to 2, we see that c1 must be 2. Now, to use the second one, you have to differentiate this. And when you differentiate this, because it's a product of two functions, you have to use the product rule. So you first have to differentiate the second one, and then plus, when you differentiate this, the first part has to be differentiated now. And that's going to be e to the negative x. If you differentiate cosine 2x, that's negative 2 sine 2x. And then sine 2x differentiates to 2 c2 cosine 2x. Okay. And then if you differentiate e to the negative x, it's just negative 1 multiplied, so you're just going to end up with the minus of this. Okay, therefore, y prime of 0, e to 0 is just 1, sine 0 is 0, so you're going to get 2c2 from the first part, and then minus c1 from the second part, because sine 0 is 0, cosine 0 is 1, so c1 is the only survivor. E to 0th power is 1. So this is what you get, and this has to equal to 4. So let's plug in c1 equals to 2 and try to solve. So let's see, 4 equals to 2c2 minus 2, and that gives you c2 equals to, if you add 2 both sides you get 6, but then you have to divide by 2, so you're going to get 3. So you got c2 as 3, and if you stop here you don't get full credit because the differential equation is asking you to find a function as its solution. So this value of 2 and this value of 3 must be plugged in, and this is the final answer. Okay, so if you stop here you don't get full credit, but if you stop here, that's the final answer. Okay, find the general solution. Y double prime minus 6y prime plus 9y equals to 27x squared. So this is a method of undetermined coefficients, and so you first need to find the complementary by doing the characteristic equation. Well, this is, again, you can complete the square and you get the fact that r is equal to 3 for both of the solutions. You have 2 solutions that are equal, or if you just have one solution from the characteristic equation, then you have to make the second solution from the first one by multiplying by x. So the y complementary solution in this case would be c1 e to the 3x, but because you only have 3, the second solution has to be obtained by multiplying by x. Okay, so that's yc. And then you have to go for the yp. For yp, you have to include all the terms that appear on the right side and all its derivatives, but just disregarding the coefficients. So I see x squared, so that must be inside my yp, x squared. And it's undetermined coefficient, so you put some undetermined coefficient a. And if you differentiate x squared, you get 2x. So x must appear, so bx. And if you differentiate x, you get a constant, so you need a c. And if you differentiate a constant, that's 0, so that's all you need. Okay, so keep in mind, to make the method of undetermined coefficients work, you include all of the functions on the right side and its derivatives. So for example, if I had this one and then plus cosine 2x or something, then you should also include plus d cosine 2x, and then if you differentiate cosine, you get sine, so that'll be e sine 2x. But then if you differentiate sine, you come back to cosine, so you don't have to add anything. So this function, if there is this function on the right side, you should include this, and you have to differentiate this. And then plus there's also other complicated things, like if you have e to the 3x on the right side, for example, then that's also duplicated in here, so you have to multiply by x. So there's some other additional rules that are more complicated. But this is a very simple case. You need the method of undetermined coefficients for this single function, so you just write the function itself and all of its derivatives. Now you want to plug this into the left side to match with the right side, so you have to compute its derivatives and also the second derivative. Plug it into the left side. So that's going to be y double prime is 2a replaced, and then y prime of p would be this. Oh, by the way, let me just put underscore p just to stress the fact that I'm evaluating the left side with yp plugged into y. And then 9y, y is this thing, so you have to multiply. And let's simplify this. You get 2a minus 12ax minus 6b plus 9ax squared plus 9bx plus 9c. And then if I collect all the like terms, let's see what we get. So 9ax squared is the very first one. And for the x's, I get negative 12a plus 9b. Right? Okay, and then for the constants, it's 2a minus 6b and then plus 9c. Okay, and that has to now equal to the right side, which is 27x squared and 0x plus 0. So that gives you the following equations. 9a has to equal to 27, and then negative 12a plus 9b has to equal to 0, and then 2a minus 6b plus 9c has to equal to 0. And solving one by one, I get a equals to 3, and then plugging that into the second equation, you get negative 36 plus 9b equals to 0, which says that b must equal to 4. And then when you plug in 3 and 4 in here, 2 times 3 is 6. 6 times 4 is 24. Plus 9c is equal to 0. And I see that c is 2. So finally we see that the yp, whose coefficients we didn't know, must be 3, and then 4, and then 2. Okay, so with this, the general solution of a non-homogeneous differential equation is given by complementary solution plus the particular solution. So it must be this complementary solution plus this particular solution. And that's it. Okay, now for the word problems. At 210 degrees Fahrenheit, water was poured over tea leaves. 4 minutes later, it cooled down to 185 degrees Fahrenheit. You like to drink your tea at exactly 135 degrees Fahrenheit. When is it the right time to drink the tea? Okay, so you have to know the Newton's law of cooling, which says that so let me just write it. Newton's law of cooling, which says that the rate of change of the temperature of an object put in an ambient background temperature it's proportional, so proportional to the constant times A minus T. So where this A is the ambient temperature, where A is the ambient temperature. So put it this way, if your object is hotter than the ambient temperature, this A minus T will be negative, so that K times something will be negative, making this T to drop because the rate of change is negative, okay? Which agrees with our intuition of how T cools, right? But if you put some food in an oven where the inside of the oven, the ambient temperature is much higher than the food, in that case, this will be positive, and the temperature of the food will go up, right? And then another thing that you realize is that the difference between the ambient temperature and the object, if it's the bigger the difference is, the higher the rate of change would it be, okay? So this Newton's law of cooling makes very much sense. Don't try to memorize this, but just try to make sense out of it. And then once you make sense out of it, then you don't have to try to memorize it. It will just be natural to you, okay? All right, so assuming that you know this, let's try to solve this. What are we doing? We are saying that oh, I forgot to do something. The room temperature is, let's say, usually 70 degrees Fahrenheit is a common room temperature, right? So yeah, without this information we can't solve this, okay? So the room temperature is 70 degrees Fahrenheit. When is it the right time to drink the tea? Okay, so if we go by that, A would be 70. Sorry about that, I forgot to include this information. Okay, so here are some of the things that we know. In our specific contest, dt would equal to k times 70 minus t, and also the initial temperature was 210 degrees. And you're trying to see, and also T of 4 is equal to 185. And with these information, you have to figure out what time it reaches 135. Okay, so let's see. This is a separable differential equation. You can divide by 70 minus t to the left side. So let's see, 1 divided by this times dt equals to k times dt. So I obtained this by dividing by 70 minus t on the left side and multiplying by dt to the right side. And you can integrate both sides. The left side is, if you differentiate 70 minus t, it's negative 1. So if you multiply by negative 1 and to make this as negative 1, it's that f prime over f integral type, right? So the integral of the left side will be negative ln of 70 minus t. Remember, f prime over f, if you integrate, it's ln of the denominator. And you need this minus so that when you write this as negative of negative 1 over 70 minus t, this negative 1 over 70 minus t really looks like f prime over f. Okay, on the right side, it's k times t plus c. Let's solve for t. First, multiply by negative. You can put plus c or minus c, it doesn't matter, it's just some constant. Exponentiate both sides, so you get 70 minus t equals e to the negative kt, and then plus c. And that's same as e to the negative kt times e to the c. And again, that trick, e to the c can be written as just some constant because c is some random value. C is some constant, random constant. So we end up with 70 minus t equals to c times e to the negative kt. Solve for t, which is 70 minus this thing. Okay, and then now what do? We now apply the initial condition. T of 0 is 210, right? So if I say 210 is t of 0, then that's 70 minus c times e to the 0th power, which is just 70 minus c. And we see that in that case, c has to be negative, let's see, negative 2, let's see, if I move the c over here and you subtract 210, 70 minus 210 is 140, okay? So that tells you that c is negative 140, and then plugging that back in, you see that t is equal to 70 plus 140 e to the negative kt. Okay, and indeed, if you plug in 0, you end up with 140 plus 70, which is 210. Okay, then next what you need to do is you have to use this fact. So we have T of 4 equals to 185. 185 equals to T of 4. And if you plug in T equals to 4 over here, you get T as 4. And from this, you need to know the value of K. So how do we get the value of K? Let me copy this over here, and we'll continue. Okay, we'll continue. All right, so we have, let's see. Subtracting 70 gives you 115 equals to 140 e to the negative 4k. And then dividing by 140, you get 115 divided by 140 equals to e to the negative 4k. And that means we have to take the ln both sides to get negative 4k equals to ln of 115 divided by 140. Okay, and this we need a calculator for, so let's use a calculator. Here's my calculator. Clear. Let me make it slightly smaller. Okay. All right, so we have ln, not that, ln of 115 divided by 140, and really, yeah, I don't know what happened. Let me do this again. It should be ln of 115 divided by 140. Oh, I see what happened. Still have trouble using this. Let me try this again. ln of 115 divided by 140. Close the parenthesis. And then to solve for k, you have to divide by negative 4. So I'm going to divide by negative 4. And that gives you 0.049118. 0.04918. So I have this value. K equals to 0.04918. And now putting that back in, we have the actual formula for the t. And this is the value we need. Put it in here. And now we want to solve the other equation, so which is, I want this to be 135. So let's see. 135 equals to this. Subtract 70, so that's going to be 65 equals 140, and then e to this power. So by dividing by 140 and taking the ln, we see that negative of this value is ln of 65 divided by 140. And therefore t should be this value divided by negative 0.04918. Okay, so let's do that again. It should be ln of 65 divided by 140. Close the parenthesis, and you divide by negative of 0.04918. And that gives you 15.6. So the answer is 15.6 minutes after the water was poured over the tea. Okay, so that gives you a good idea. If you're a tea drinker, I guess you pour the water and you want to let it sit for 4 minutes. And once the tea is ready, you want to wait for another 11.6 minutes for a great tasting tea. Okay, thank you.